presentation.
Thank you. Yeah, so I had to stop the screen sharing to start recording, but I see recording is in progress, I suppose. Right, just to confirm. Yes, it is in progress, and this is the slide. I hope it is visible to all of us. Okay, perfect. Without further ado, let's begin straight away. Welcome to the first talk on the student talk series. I'll be presenting my paper, Legendre-SNN on Loihi-2, that was accepted at the recently concluded MLNCP workshop in Europe this year. So as part of this talk, I'll be focusing on how to program the Lakemont course, which is quite a valuable resource, but quite minimal technical documentation is present, how to program them and utilize them in your resonance. I am Ramashish Gaurav. I'm a PhD student at Virginia Tech. I am majoring in computer programming and engineering field, and my supervisor is Dr. Yang Cindy Yi. Yeah, and the equation that you're seeing on the left is a foundational equation of the state space model, the state transition equation. We'll be, as the talk progresses, we'll be looking more into the details of how to implement such a state transition equation on the Lakemont course. Okay, let's start right away with the problem definition. So the SNN models, as you may know, may consist of non-spiking components apart from the usual spiking layers. And the spiking layers are, of course, very easily deployable on the Loihi-2 Neuro course. So the non-spiking component, an example for that would be the reservoir in the Legendre-SNN. So how does one implement a non-spiking component on Loihi-2? Especially on the low power Lakemont course. So the objectives of this talk is that at the end of this, we would learn how to what is first of all the Legendre Delay Network, and how to implement a quantized version of Legendre Delay Network on the Lakemont course. Then we will learn how to implement rate encoding on the Lakemont course. And learn how to, and overall, the goal of the task is to learn how to program the x86 Lakemont course of Loihi-2, so that you can use whatever was presented in this talk in your own work to implement your non-spiking operations on low power Lakemont course instead of on the CPU. Great. The overview, I'll start with an introduction to Loihi and Lava. Then I'll talk about Legendre Delay Network, and finally the Legendre spiking neural network on Loihi-2. And then I will dive into the programming details of LDN, the Legendre Delay Network, and the encoding process on the Lakemont course. So this talk is pretty much, or I would say quite technical in nature. The paper itself was very technical in nature. So we will be looking into the Lava programming details of implementing the signal input process on CPU, and then the Lava program for implementing the quantized LDN and encoding process on the Lakemont course. And eventually a short form of the Legendre spiking neural network, that is to how to collect spikes from the LDN and the encoding process on the Lakemont course. Then we'll finally look into the Legendre-SNN's results on the Loihi-2 Neuro course. Great. So Loihi, I'll be very quick in initial few slides, like 5 or 6 slides, because I'll be focusing more on the programming aspects of the Lakemont course. Loihi is Intel's highly coveted neuromorphic research chip. The first was Loihi-1 that was released in 2018. It consists of 3 x86 Lakemont cores and 128 neuro cores, each having 1024 CUBA neurons where you can deploy your spiking networks. Loihi-2, released in 2021, it consists of 6 x86 Lakemont cores and 128 neuro cores, but this time each having 8096 CUBA neurons. The CUBA units, the current-based models, they can be adapted to implement integrate and fire or leaking integrate and fire neurons. Coming to Lava, it is Intel's neuromorphic library to build SNNs and program the Loihi chip. It supports deployment of spiking networks on CPUs, GPUs, and Loihi, as many of us already know here. if someone wishes to program SNNs in Lava, then there are 4 broad concepts that we need to be aware of. The first one is the process. It's a programming construct in Lava, which defines the hardware independent interface. Then you have got the process model, which corresponds to one process. It defines the hardware dependent implementation. And then the Loihi protocol, which consists of 5 different ordered phases to synchronize the processes. Then you have got run config, which is a configuration to choose the backends of the deployment of your SNN. That could be a CPU or a Loihi or the neurocore. So a process can have multiple process models, as many of us would know. For example, one process would have a process model to be deployed on CPU, and the same process would have another process model to be deployed on the Lakemont cores. Lava supports 3 different types of process models. The first is the Pi Loihi process model, which can be deployed on the CPU. Then you have got your C Loihi process model, which can be deployed on the Lakemont cores, and that's exactly what we'll be using in this talk. And you also have got your NC process model supposed to be deployed on the Nero cores. Let's dive right into the Legendre Delay Network. This is an example of a state space model that is used to approximate a delay of a univariate input signal. So say like you have got your input UT and the delay is YT. It implements a function f such that when you pass the input UT to it, the output YT is approximately equal to the delayed version of the input UT. That is, the signal here is delayed by some theta time steps. In the above equation, well, f delays UT by theta time steps. In the picture here on the right-hand side, this shows the functioning of an LDN, the input-output of an LDN. You have got your input UT, which is colored in blue, and then you have got your ideal delay, which is in orange curve, orange line, and the computed delay by the LDN, which is in the green color. So the computed delay, that is the green and the orange line, they pretty much overlap. So that means the LDN is pretty good in computing the delay of an input signal, but of course dependent upon its hyperparameters, which we'll be looking in a few slides. So the LDN implements the delay function f via a set of state space equations in discrete time. So these are the set of state space equation. The first one is the state transition equation, and this is the state observation equation. Here the UT is the input to the LDN, and xt here is actually the state vector of the LDN, which is a d-dimensional state vector. And yt here is the output from the LDN. And the state matrices A, B, C, and D are sort of predefined. You need to define them. And here A is a D times D square matrix. B is a d-dimensional vector. C is another d-dimensional vector. And D here, by in the definition of LDN, is set to 0 or is obtained as 0. The values of A, B, and C matrices can be found in the paper referred as 3, which I'll show in the last slide. This picture here shows how the state vectors of LDN look like. I've shown you here the input U, the output Y. What about the state vector X, right? So here you can see for each time step of the duration of the input U, you happen to extract some features xt, and those are plotted here. So this is the example of an 8-dimensional state vector. It's difficult to really see. There are 8 different lines in it, but take my word, there are 8 different lines in it. Okay, continuing on that, this is a much clearer picture or a pictorial representation of the LDN. You have got your input UT. It has to be multiplied by B, and then the current time steps state vector X is multiplied by A, and eventually you sum them up to obtain the next time steps state vector. So note here that the Legendre-SNN employs the component of the LDN, which is within the dashed rectangle. So only this equation, that is the state transition equation, is the one that Legendre-SNN employs. It does not implement this computation of the delayed output. That is multiplication by C. Rather, just AXT plus BUT is equal to XT plus 1. Okay, the LDN in Legendre-SNN, it is a non-trainable component, and hence it's called the reservoir here, where the A and B matrices are static. You do not train them. And only the state transition equation 1A in the previous slide, that is just this particular equation, not this one, is used in the Legendre-SNN as a reservoir. The tunable hyperparameters of the LDN here are the state vectors xt's dimension or order t. So you can tune it for different values of t, d, and the max delay or the memory encoding window theta of the LDN. These hyperparameters d and theta determine the quality of the state vector xt, and henceforth the temporal features is what we will call them here. Okay, now let's talk about Legendre spiking neural networks right away on the Loihi-2 chip. Legendre-SNN consists, this architecture comprises one LDN followed by an encoding layer, hidden layer, and an output layer. It's pretty simple, very basic reservoir-based model where you have got just one layer of recurrence here, the LDN. This is an input node which sends a signal to the LDN. It extracts temporal features which are sent to the encoding layer. You encode them to binary spikes here, which are, so this layer is dense all-to-all connected to the hidden layer, and the processing happens here, some nonlinear transformations, and eventually ending up here at the output layer. And then you can infer the classes from the output layer neurons, which through the spike rate of the output layer neurons. Okay, so the LDN here inverts, it computes or extracts the features xt from the input ut, and each scalar of the state vector xt is duplicated and rate encoded via the 2-neuron encoding system. The reason it is duplicated, each scalar of xt is duplicated, is because they could be positive and negative. So you need to have a 2-neuron system such that one neuron is sensitive to the positive sign of the scalar and the other neuron is sensitive to the negative sign of the scalar. So you need 2 neurons in a pair to encode the xt, each scalar of the state vector xt. The encoding layer has, as by definition, has only 2 times d number of integrate and fire neurons, and the hidden and the output layer, they comprise 3 times d, and the number of classes equal to the number of Cuba neurons here. So these Cuba neurons are tunable in the sense that you can tune their voltage and current decays. So please keep this architecture in mind, and we can remember that through an abstract representation of it, because this architecture is, this representation is what we'll be referring to in the next few slides on mapping this Legendre-SNN on the Loihi-2 chip. So you have got an input layer followed by the LDN, and then you have got the encoding layer, and then eventually one hidden layer, and then the output layer, and eventually the classification layer. So coming to the training and evaluation, a bit of small notes on that. For the Legendre-SNN, it is trained off-chip on GPU using Lava's Slayer API, and only the hidden and the output layers are trained. That is, hidden and the output layers. These connections in the black color, they are the only ones which are trained. The features xt are extracted on the CPU. That is, you can implement this LDN right away on the CPU, simply extract them and send those features to the encoding layer, such that the SNN on the encoding layer onwards, this, as I mentioned before, is the only SNN to be trained. This Legendre-SNN is evaluated off-chip on CPU, and you can as well as evaluate it on Loihi-2 as well, which is the focus of this talk. Continuing on that, let's now talk about the training and evaluation hardware backends of the Legendre-SNN. So this picture shows you the hardware backends for training. You have got your input, LDN, and the encoding layers, which can be implemented on the CPU backend, and the hidden and output layers could be trained on the GPU, and the classification is done on the CPU. This picture shows you the hardware backends for evaluation of the Legendre-SNN on the neuromorphic chip, on the Loihi-2 neuromorphic chip. So here you have got your input and classification, because these are the IOs of like inputs and outputs of the Legendre-SNN. So they're deployed on the CPU, whereas the LDN and the encoding layers are deployed on the Lakemont cores, and the hidden and the output layers are deployed on the Neuro cores. So coming to how to map individual layers of Legendre-SNN processes as lava processes on the Loihi-2 for evaluation. This picture shows you exactly that. Please note that this picture and this one here, these two figures are color coded, in the sense that you have got your input signal to LDN process here, a lava process, which is responsible for implementing the input layer. The LDN encoding to spike lava process is responsible for implementing LDN and the encoding layers. And the NetX-SNN process is simply the trained hidden in the output layers. And the output spike to class process is a classification process. So this, and yeah, also definitely keep this in mind that this mapping was done after you have trained the Legendre-SNN on the GPU. So this mapping is only for inference purposes on the Loihi-2 neuromorphic chip. The input signal to LDN process sends its signal to the LDN encoding to spike process. And once these, once the state vectors or the temporal features from the signal has been extracted and encoded to spikes, those spikes are sent to the NetX-SNN for constituting this hidden and the output layers, and eventually through adapters, you get them to the output spike to class classification process, simply to infer classes from there. Coming to the data sets and hyperparameters, this Legendre-SNN was trained on GPU and evaluation was done on CPU as well as Loihi-2. And it was done on the entirety of the 15 univariate time series classification datasets. So you can obtain them on the timeseriesclassification.com website. All the datasets are publicly available there. The values of D were tuned between 4 and 24. It was just a calculated choice here. Between 4 and 24 different values, 8 different values, and theta was tuned with 110 to 150 time steps of, corresponding to the, of course, the duration of the input signals. And decays here correspond to the neuron and voltage decays. They were tuned with values 0.0, 0.10, and 0.20. Okay. Before we move on to the actual lava implementation, let's do a very brief and an intermediate recap. I think I'm right on time here. Yeah, so the Loihi-2 chip has got 6 x86 Lakemont cores that execute C code, classic C code, C SNPs. The Legendre-SNN is composed of non-spiking reservoir called LDN, followed by a spiking network composed of encoding, hidden, and the output layers. The reservoir, that is the LDN, uses a state transition equation to compute the temporal features, that is d-dimensional xt vectors that are rate encoded to binary spikes. The LDN is characterized by two hyperparameters, d and theta, on which the non-trainable matrices A and B depend upon. And these matrices are of course, in the state transition equation. The hidden and the output layers are trained via the layer lava's Slayer algorithm. And the Legendre-SNN, once it is trained, you can map it to 4 different processes for evaluation on Loihi-2. The first process is input signal to LDN, followed by LDN encoding to spike. And then it's followed by NetX-SNN and followed by output spike to class process. Good. We will be discussing more once in the discussion round. So let's please do note your questions if you have any, and we can get back to them later. Now let's talk about the programming details of the LDN and the encoding process on the Lakemont course. So here I'll try to be slow and yeah, go into the details of it. So let's now focus on the core of this talk. That is how to program the Lakemont course. And in this talk's example, it's about implementing the LDN and encoding layers. So whatever you would eventually gain from this talk, I'm pretty sure you should be able to apply the same for your different kinds of SNNs to implement any kind of non-spiking operation on the Lakemont course. So here it's specifically in the context of how to implement the LDN encoding to spike process on the Lakemont course. For the purpose of this talk, let's consider that we are collecting spikes from the LDN encoding to spike process on the Lakemont course. The reason I want to constrain myself for implementing just one or two different processes on the Lakemont course for this purpose, for this talk's purpose as well, because Legendre-SNN, if we really go into the Lava details, implementation details of Legendre-SNN, it will probably go beyond the talk's limit here. So I'm just taking an example of, say, like you implement a LDN and the encoding process on the LMT course, and then just simply collect the spikes, because eventually this is a part of Legendre-SNN nonetheless. You will here you're collecting the spikes, and in Legendre-SNN you simply forward those spikes to the next connected processes. So here is a pictorial representation of the two processes that I'll be implementing here and are sort of like talking here about its implementation in this talk. You have got your input signal to LDN process. It has got two output ports. So through one port, it sends the univariate signal UT, and the other output port, it sends the labels to the output classification process, which we'll not be talking here, but you can definitely look into my paper or the code itself and on GitHub, and feel free to get back to me in case you have any questions there. So the output signal, the signal which is being fed from the input signal to LDN process is received in the LDN encoding to spike process. It has got one input port and another output port. The input port simply receives the sent sent signal, and the internal variables here do their magic of transforming this input signal to the state space, to the state vectors, and then eventually encode them to binary spikes. Now, those binary spikes have to be sent to the next connected process, which is Legendre-SNN, or we can simply collect it, as I mentioned, and that will be done through the spike output process. In words, the input signal to LDN, this is a process to feed the input signal UT to the LDN encoding to spike process. And this particular process, input signal to LDN, has got its process model, a pi Loihi process model called pi input signal to LDN model that runs on the CPU. Now, this LDN encoding to spike process, this is a process to extract the temporal features xt from UT and then encode those to spikes. It has got two different process models. One is a C Loihi process model named as C LDN encoding to spike on LMT model. My apologies for having such big names, but I wanted to be as descriptive as possible in my code as well. This process model runs on the Lakemont course. And the another process model for LDN encoding to spike process is a pi Loihi process model, which is supposed to be run on the CPU. Now, in your implementation, when you deploy a network, an SNN on Loihi-2 chip using Lava, then only one of the process models is active at a time. So here, in my implementation, so we'll be talking only about C LDN encoding to spike on LMT process model, which is active when such a network on the Lakemont course. This LDN encoding to spike process on the Lakemont course. Had I had chosen to deploy this LDN encoding to spike process on the CPU, I'd have simply went ahead with this pi Loihi process model here. Cool. Now let's talk. I think these are the code details, yeah, of implementing this signal input process first. So here I was debating how to present it in a best way possible. Given that we rarely go through code in our presentations, so what I've tried to do is I have picked up some uh, important code snippets from the actual implementation that can be found on GitHub, and then I also talk about its key takeaways. Like instead of going through line by line on each particular like in each code snippets, we'll just focus on some particular lines which are important to understand in this talk. And of course, please feel free to note your questions here as well. And as we progress in the discussion phase, we can discuss more about that. So this is the input signal to LDN code, the snippet. Here, this is a process. So the key takeaways here is that this is a generator process to send a test signal through the SIG output port and the labels through the label output port. Now, each test signal's duration, given that you are feeding one complete signal, and then you would eventually iterate to the next input signal, and so on and so forth, eventually through the entirety of the test data set, right? So you're feeding one scalar of one signal at a time. So the entire duration of that test signal, for example, for the ECG 5000 dataset, each test signal comprises of 140 time steps. So that 140 time step is stored in the per sample time step variable here. And we will be using this variable to do quite a lot of operations to switch or to iterate to the next test signal. First test signal has been processed, and so on and so forth. This process iterates over the test signal index, which is current index, as we will look into its implementation, and stores the current test signal, that is the existing test signal that you want to process, in the signal input variable. Now, this variable is, as you can see here, it is a NumPy array internally. Of the dimension of, say, NTS number of time steps, for example, here 140 time steps. So that is this entire SIG input variable is 140 time steps long, or 140 indices are there, the length of this array. Coming to its corresponding pi Loihi process model, the pi input SIG to LDN model. So as you can see here, it implements the process input signal to LDN, follows the Loihi protocol, and this process model requires the CPU because it is supposed to be deployed on the CPU. The key takeaways: all these scaled and quantized test signals and corresponding labels are stored in the test X and test Y variables, which you can populate by calling a function external to this pi input signal LDN model. So proceeding ahead to the implementation of the actual Loihi phases here, the first phase that we need to implement is the run SPK phase. The key takeaways is that the run SPK phase runs every time step. And please note that the time step in Lava starts from 1. And that's why you have got this sort of a very different line here, which denotes that the entire signal is processed. So time step variable starts with 1, it continues iterating and adding it to itself, 1, 2, 3, 4, 5, 6, so on and so forth. And eventually when it reaches to the 140th time step, or 141th time step, or 141st time step. So and per sample time step here, as I mentioned in this example, if it is 140, then that means the entire signal has been processed, right? So its remainder will be 1. So it has to be reinitialized. Like you have to set the signal input again to 0, and eventually this will be this signal input will get populated in the next phases that will come later after this run SPK phase. So every time step during that 1 to 141st time step, a scalar value is sent through the SIG out port here. So you get the scalar value, here and send that through the SIG output port to the connected process. Then you have got the postguard phase. And the key takeaways is that if the simulation time step is 1 plus multiple of test signals duration, that is this exact condition, if this exact condition is satisfied, then it returns true, which means the run post management phase will be executed. And it also implies that the entire current signal has been processed. So the time has come to update to the next test signal. So here you've got your run post management phase. The key takeaways here is that when the post guard returns true, when this function returns true, run post management will be evaluated. It also implies that one test signal has been processed. So you got to update the signal input variable, which stores the signal, as you can see here from the test X, that is the test signals. For the current index, it will be stored in the signal input. And eventually your current index will also be updated. That is, it will be iterated to the next signal, next test signal that you'd choose. Okay, let's take a brief pause from the code and look into the implementation, the quantized implementation of the LDN and the encoding process on the Lakemont course. So the quantization constraint on Lakemont. So the problem is the Lakemont cores support only 32-bit integer operations, and those are the ones that are executed on Lakemont cores. That is, the operations and the variables have to be subsequently quantized for their implementation, which implies that you also need to feed a quantized input UT to the process on the LMT that we saw in the previous slide, that where we were scaling and quantizing the input UT to be sent to the LDN encoding to spike process on Lakemont core. Coming to the quantization method, one common way is to simply multiply the floating point values by a power of 2, say 4096, and then clip away the fractional part. So for example, this mathematical expression denotes quantization in my paper's context. You have got your input UT, you multiply that with P, a scaling factor, and then these angular brackets represent clipping away or rounding away of the values to a quantized, scaled and quantized value, which is denoted by U bar T. So here U bar T is quantized, and this denotes rounding. Using the same method, you can also obtain other quantized variables, for example, the quantized state matrices. So here you have got your real value, continuous real valued A, and then you multiply that by P and again round it off, and you obtain the quantized A bar matrix. You can apply the same operations on B and the state vector XT as well, because you are implementing this state vector XT on the LDN, sorry, on the Lakemont core, and that's why it has to be quantized, and just A bar, B bar, and X bar T represent the quantized values of quantized values of these variables, and without bar like on top of it, like A, B, and XT, they are simply continuous valued. Now let's talk about quantized LDN. So the equation for the quantized LDN, the state transition equation looks like this. You have got your U bar T multiplied to B bar, and it is added to X bar T multiplied by A bar, but you also have got your X double bar one. The next time steps state vector has got double bars on it. And the reason is because this particular variable has the contribution from the factor P twice, because here is a P and P two factors, here also P and P two factors. So you need to scale it back to X bar T plus 1 for subsequent computation of the state vectors. And you can do that using the seal. First of all, you just divide the X double bar T plus 1 by P, the scaling factor, and then simply take a seal operation in my case. And coming to the quantized rate encoding of these computed state vectors here. I'm following the neural engineering framework equations. So here, as X bar T is quantized, you also need to account for quantization in encoding process too, right? So the input is quantized, the state vectors are quantized, and when you encode them, you have to encode those quantized state vectors. So you have to also account for quantization during encoding as well. So the so the neuron equations, as I mentioned, the if neuron equations that I'm using in the encoding layer, they are picked up from the neural engineering framework theory. So you have got your current J and the encoder values E multiplied to X bar T. Alpha is the gain here, beta is the bias here. Not much of a thing going on here, but eventually you're able to get a current value from the of the state vectors, and then you feed that current to the voltage. You account for that in the if neurons voltage, which are also quantized, and then you can pass the difference between the voltage and the voltage threshold to a Heaviside step function theta to obtain binary spikes. Right. Now let's talk about implementing the Lava programs to implement quantized LDN and the encoding process on the Lakemont course. This is the code for the interface or the process, LDN encoding to spike process. And well, a lot is going on in here, but we'll, as in the previous slides, we will focus only on the key takeaways. The first one, the scaled and quantized A and B matrices, that is A bar and B bar, they are stored in A prime and B prime variables here. So you can obtain these matrices from, again, an external function here, get scaled A prime and B prime matrices and store them here. Then here, just a reminder, as I mentioned, it has to first of all not only obtain the state vectors but also encode them. So you also need to have the gain and bias values, which are stored in G gain and G bias values for encoding the state vector X bar T. Then you also have the threshold voltage, that is GV global voltage threshold, which for the Heaviside step function, which is also scaled and quantized, as you can see here. The global voltage threshold, scaled and quantized. I mean, here the voltage threshold, I have chosen it to be 1. So if we just scale it up, it is considered to be quantized. There are 2 ports here, a signal input port that accepts the UT from the previously described input signal to LDN process, and the output port, which is supposed to send the binary spikes to the next connected process, or you can simply collect the spikes as well. So yeah, the SPK output port to send the binary spikes to the next connected process. Okay, now let's talk about its C Loihi process model. So again, a small reminder, there are 2 different process models that I have used in my code, one for CPU and one for Lakemont course. Since we are talking about programming the Lakemont course, I'm just talking about the C LDN encoding to spike on LMT model, which is a C Loihi process model to implement on the Lakemont course, to implement the LDN encoding to spike process on the Lakemont course. So here, as you can see, it implements the process LDN encoding to spike using the protocol Loihi protocol and requires LMT. So the previous process, input signal to LDN, required CPU because it was implemented on CPU. This requires Lakemont course, and hence I've mentioned with a macro here, LMT, which is a Lava-defined macro, which signifies that yes, this has to be implemented on the Lakemont course. Great. Coming to the key takeaways, the signal input is defined as a C in port, and SPK output is defined as a C out port here. And all the data types here, as you can see here, they are all of type Lava C data type dot integer 32. That is just quantized integer 32 operations. Coming to the actual implementation of the quantized LDN and the encoding, that is done in this C file, LDN encoding to spike on lmt.c. And you should definitely note the name of the C file here. You can choose any, but then you have to create the C file within the same directory as this Python file. And you also need to create a corresponding header file with the same file name, that is LDN encoding to spike on lmt.h. right? So if you happen to implement any your own specific non-spiking operations, so you can implement the C file here, and then you also need to create a corresponding header file for the same. Coming to the header file, how does it look like? In my case, for implementing the Legendre Delay Network on Lakemont course, you have got your Loihi protocol phases. The key takeaways are that you define the interfaces of the Loihi protocol phases here that you plan to implement in the C file, and that's it. That's all you need to feed or write in the LDN encoding to spike on lmt.h header file. Now let's talk about the contents of the C file, the actual C file where you implement your LDN and the encoding process on the Lakemont course. So the key takeaways, well, you should definitely include your header file. Note that the file name is same as that of the C file with a .h extension to it. And another header file called predefs underscore CLDN encoding to spike on LMT model.h. So the thing is, your specific C Loihi process model may have a different name, but whatever name is that, you just need to write it down here as well and .h and include both of them. And this, although the header file on the first line that you will explicitly write, the header file in the second line, you have to, so this is automatically generated for you. You just need to include it here. And this header file sort of contains all the C versions of your variables that you defined in your process. So here you have got your SPK guard and post guard Loihi protocol phases. The key takeaways here are that you implement the guard phases in here, and you can pass a run state pointer to it. Now, this pointer has quite a lot of information in it. One of them is the time step variable. So you can access the execution time step of Lava processes running on the Lakemont course or the Neuro course using the time step attribute of this run state pointer. And the SPK guard here is returning one every time step. So it enables, and that is because you want the run SPKs to execute every time step. And then the post guard ensures that the run post management phase is executed after the entire signal has been processed. So you might be familiar with this expression that once the entire signal has been processed, let's jump or iterate to the next test signal. Here you have got your run post management phase, which sort of like zeroes out the global state vectors and the voltages. The key takeaways in the run post management phase, you can these global state vectors and the voltages, they are reinitialized for the next updated input signal. You can simply define a function to that, and you can call that function within the run post management as well to keep your things clean. Continuing on the C file itself, now let's talk about how to the implementation in the run SPK phase itself, like where you are computing, where you are not only computing the state vectors, but you're also encoding them to binary spikes. The key takeaways, you can use the receive vec dense API every time step to accept an input UT into the signal, into a local variable here, which is input. That signal, that scalar UT, if you remember, was passed through the signal input, sig input port. So the value here is stored in this local variable input, and which is defined here, right? And in this next subsequent code snippet, here I'm computing as you can see, it's a fairly classic example of matrix vector multiplication. I'm simply doing some matrix operations here, matrix vector multiplication here, and the key takeaway is that you can use the existing state vector, the global LDN state that you saw in the previous slide, to compute the A bar, X bar, T matrix, the quantized multiplications, and you can use the current input, which is stored here, to compute the P bar, U bar, T matrix here. So once you have computed them, the multiplications have been performed, you simply need to add them up to compute your next time steps state vector, which is done exactly in this code here. Although the key takeaway is you need to scale it back, right? So you need to when you've computed the state vector for the current time step, you can scale it back through integer division, and then of course the ceil function on it. That is, you're computing the next time step state vector. Now let's talk about, given that we have now obtained the next time steps state vector, we can simply encode them to binary spikes, right? And this is the code that does it. So here the key takeaways, you can rate encode the computed state vector to binary spikes, and you can store that in a, here I'm storing it in a spike data variable here. I'm iterating through each and every element of that state vector. Here is the current equation. On line 5 is the voltage equation, and you can simply just define the Heaviside step function here in this. Like if the voltage is greater than the voltage threshold, simply it outputs a spike, and that is stored in spike data variable, spike data array. Now, once you have obtained the spikes, you would like to send that to a next connected process, and you can use the send vec dense API to pass on your values in the local variable, that is spike data, to the spike output port. So the key takeaways from this, the overall key takeaways from this LDN encoding to spike on lmt.c file is that you can use receive vec dense API and send vec dense API to interact with outside processes than the Lakemont course. Notes, while sending an input UT from the CPU to the Lakemont core, you do not need an adapter. And one can process and encode the input UT to spikes on the LMT via quantized operations. And while sending the spikes from the Lakemont cores to the Nero cores, you again do not need an adapter. Now let's talk about collecting spikes from the LDN and encoding process on LMT, sort of like combining both these processes together. So here I've initialized the input signal to LDN process, which is supposed to be deployed on CPU, the LDN encoding to a spike process, which is supposed to be deployed on the Lakemont cores. And you can just instantiate these processes, and you can just connect them directly. As I mentioned, you do not need an adapter. You just connect them directly. Now, here you're defining the Loihi-2 hardware config, and you're mapping these processes to their corresponding process models. So the LDN encoding to a spike is mapped to a C Loihi process model to be deployed on Lakemont cores, and input signal to LDN is mapped to a CPU process model. So you can create a run config, map their process to the process models, and you can also create an object of this monitor class to simply probe the spike output port with respect to the spikes in it. So these SIG, and then you can just simply run either of these processes, and as they are connected, upon running it, both the processes run on CPU and the Lakemont cores, the corresponding processes, and you can just obtain the spikes. Finally, let's look into the last slide, the Legendre-SNN's results on the Loihi-2 neuromorphic course. But before we do that, there is a bit more information here with respect to how accurate is your quantization process. So if you happen to deploy your own non-spiking operation on the Lakemont core, you'd like to check, is it accurate? Is it doing exactly what I want it to do? And for that, this example here, which I'm presenting, could be used in your case too. So for us, since we implemented an LDN as a quantized operation, quantized model on the Lakemont core, let's say that for one particular value of d and theta, you implement a continuous valued LDN and encoding process on the CPU, denoted by CV CPU pi, which is continuous valued on CPU using a Python implementation, and then implement the quantized LDN and encoding using Lava, denoted by quantized LMT and Lava. And then you can obtain the spike trains from the continuous valued implementation that was on the CPU, because it's very easy, and the quantized implementations as well, like on the Lakemont course. And then you can compute the spike distance or synchrony metrics between those spike trains to figure out how how good the quantization was. In my case, I have used Victor Perpetrar distance denoted by VPR dist, the ISI distance metric denoted by ISI dist, and the spike synchrony metric denoted by SPK sync. So I've used 3 of them, and the details of those could be found in the paper referred as 8. Now, of course, let's talk a bit about these metrics. So for the VPR dist and ISI distance metrics, if they are close to 0, right, then that means the spike trains match. That means the spike trains from the continuous valued and from the quantized, since they matched, that itself implies that yes, the implementation of the continuous and the quantized values, so quantized models are pretty much the same. And if the spike synchrony metric is high, so higher the value, better the synchronization, and that means both the quantized and the continuous valued models match. So in this figure here, this is so this figure represents the metrics from the VPR dist and the ISI dist and the spike synchrony between 2 different implementations of LDN. One is the continuous valued LDN on the CPU and the quantized LDN on the Lakemont course. So the spike synchrony metric, as I mentioned, higher the value, better the synchrony, or more close the quantization, or more accurate the quantization. So here you can see the red line or red curve. The broken line is pretty close to 1. And here the VPR dist and the ISI dist, these lines are also pretty close to 0. That means pretty good, pretty accurate quantization was happening on the Lakemont course compared to their continuous valued implementations. Now this line, this plot is with respect to the quantized implementations. Now this time on the CPU as well as Lakemont course. So I also sort of evaluated, let's see how good is like if at all my CPU implementation of the quantized LDN matches the LMT implementation of the quantized LDN. So in this case, the the spike synchrony metric is all one for different LDNs on the x-axis. So my apologies, I did not explain what the x-axis meant. Is that there are 24 different LDNs for each particular LDN. It just denoted the spike synchrony or the spike distance metrics. So for 24 different LDNs, you can see these spike synchrony metric is pretty close to, it's exactly 1. And these values are exactly 0. That means my quantized implementation on CPU as well as LMT are same. Now, the finale of it, the results. So on the columns, you are seeing different data sets, all the 15 time series classification data sets. And on the rows, you are seeing different implementations of the Legendre-SNN. We should rather focus on the last row, which is the Legendre-SNN's implementation on the Loihi-2 hardware. So L2 hardware it shows it means it is Loihi-2 hardware, the physical hardware where you deploy your Legendre-SNN. And the LSTM FCN is an architecture which was published in 2017, 2018, which is one of the quite classic architectures for which benchmarked on 85 time series classification data sets. So I'm comparing with that. The LSTM FCN is composed of an LSTM layer and 3 fully convolutional networks. So compared to that, you can see that the Legendre-SNN on the Loihi-2 chip, its energy efficient SNN, outperforms the LSTM FCN, which was deployed on a GPU on 3 out of 15 data sets. So yeah, we are gradually getting closer, or sort of there's a silver lining here that when we talk about the SNNs do not outperform ANNs or deep learning networks, but slowly and gradually we are catching up to that. And these results were quite encouraging for me to see that, yes, we are able to outperform LSTM FCN on at least 3 out of 15 data sets for worms, for worms 2 class, and for meat and meat class. And in fact, by quite a lot, quite a large margin on these data sets. And in a few cases, we are quite close to the LSTM FCN's accuracy. For example, in wafer class, in Ford A, yeah, quite a lot. Yeah. So yeah, that concludes my talk. Thank you very much for being online here. Yeah, amazing. I think I'll just go back to the slide here. Yes. I'm open to questions here now.
Okay, that's perfect. Ramesh, I can maybe just fire one question before I unfortunately have to head out. But so thank you very much for the talk. I think it was really, really interesting. And it's very fun to see the practical details of how this works, right? And I've heard
Indeed.
about the Loihi architecture, and I sort of get how it works, but it's great to see how this specifically works in